when E is modular or E has complex multiplication. So I won't explain what it means for E to be modular, except to say that it was proved in the 90s that every elliptic curve over Q is modular, which was a huge deal. So any elliptic curve over Q, this deserves to be called an L-function. But that's not known in general. I'm going to prove it for curves with complex multiplication, and it will follow from Deuring's theorem, which says this is the same as the L-function of some Hecke character, because those guys do have functional equations. Great? Okay, so, yes. So now let's just sort of write down, instead of thinking of this abstractly, let's write down an explicit, oh, I didn't finish my sentence, but you asked what the Tate module is. In order for Frobenius to act, I need the action of Galois of the Tate module to be unramified at P. Otherwise, it doesn't make sense for Frobenius to act, because Frobenius lives only in the maximal unramified extension, right? However, the criterion of Neuronhagen-Shafarevich says that, in fact, the Tate module at L will be unramified for any prime of good reduction. So this is sort of the technical point, that I should take the IP invariance before there's an action. So let me just write out what this is. So these computations are in Silverman's first book. By the way, all of this talk comes from Gross's thesis, and if you want to check the computations in that, Silverman's books have them all. So let's just write down what these local factors actually are. They're going to be just 1 if E has additive reduction. So that means when you reduce the curve mod P, you get something singular, you throw out the bad points, and you're left with some group, and your group turns out to just be GA, the additive. It's going to be 1 minus the norm of P to the negative S, according as to whether E has bad non-split or split multiplicative reduction. We're not going to talk about curves with multiplicative reduction, so I'm not going to explain what that means. And finally, for most primes where the curve has good reduction, this is going to be equal to 1 minus AP norm of P to the minus S plus norm of P to the minus 2S plus 1, where AP is just norm of P plus 1 minus the number of points on the reduction of the curve level. Okay. So that's a straightforward computation of this characteristic polynomial, and details are, say, in Silverman's book. And I think chapter 4, is that right? First. Yeah, I think it's in chapter 4. Okay, when he talks about elliptic curves over finite fields. Okay, cool. So questions? Okay, so everything I've said is true for any elliptic curve, but now I want to talk about elliptic curves with complex multiplication. So let's take an elliptic curve E over F. Right. Okay. And what I want is for the endomorphism ring of E to be not equal to Z. So what does this imply, right? In any Abelian group whatsoever, you have Z as endomorphisms because you can add something to itself like 13 times. But this means that they're sort of extras. And it's just a fact that there's just not that many possibilities for the endomorphism ring. And that if it's not Z, it's going to be O, where O is an order in an imaginary quadratic field. So
F is not finite then.
What do you say?
So you assume
yeah,
F
is always a number field for the whole talk. Yeah.
Okay.
Yeah, F has characteristic 0. Otherwise, there could be.
Yeah, I guess it didn't make sense to talk about L functions if that's.
Yeah. I'm only considering F to be a number field for the whole talk. Okay, So that makes it an order in some imaginary quadratic field. If you haven't encountered orders before, this just means it's both a subring and a lattice. So it's got full rank, it's got rank 2, but it's a rank. And if you still don't like that, in just a moment I'm going to assume that it's the ring of integers. So it's just the ring of integers in some imaginary quadratic field. And what do I mean when I say equals, right? Like, is there a canonical isomorphism, right? And the answer is yes. So I'll explain this rule with examples. So I can pick a translation invariant differential omega of E. And I can demand that if I have an endomorphism alpha, that alpha upper star of omega is equal to alpha omega, where this is the image in Q bar, and this is the endomorphism. So I find it hard to think of this rule without an example, so let me just give an example. So here's the example. Right, if the elliptic curve is given by a Weierstrass model, y squared equals x cubed plus x, so this is just over q. Well, we'll let it be over q bar. We'll let it be over q adjoint. Okay. So like the map that sends y to iy and x to negative x, just doing the algebra out, is an endomorphism of the curve, right? And so let's call this map alpha. So then what should alpha correspond to? Let's just take the differential dx over y. So alpha upper star of dx over y is just going to be d of alpha y, or sorry. This is, so dx over y over x. Yeah. I'm sorry, I should think of this as dy over x. That's the standard way to do it. I don't know why I wrote it the other way. Okay. Okay, so this is d iy over minus x. So this is negative I dy over x. So the point is that the canonical isomorphism sends my alpha to negative I. That's it. So the point is, just sort of staring at this, all you would really realize is that it has order 4. So you'd know that your endomorphism ring had to be Z bracket I, because that's the only order that satisfies that. But then to actually think of this endomorphism ring as living inside of Q bar, you have to use this rule. Okay? All right. So the computation which you can do is to determine the degree of an endomorphism alpha in terms of the guy who lives inside of Q bar. So let's let K be the field inside Q bar generated by O. So yeah, it's a little pretentious. It's just the imaginary quadratic field that the order lives in. Right. Then you can compute, I'm not going to do it, that the degree of an endomorphism alpha is just the norm from K down to Q of alpha, now viewing alpha actually inside of Q. Okay? So in characteristic 0, this isn't a very difficult computation because you can use the complex parameterization of the curve. Okay, cool. So now I want to relate this to characters. Okay.